Hello everyone. Today I am going to discuss the second part of the unit 2 of subject pharmaceutical organic chemistry third. In this part we will discuss about the methods of determination of configuration of geometrical isomers. As far as the classification of isomers is concerned, they are classified in stereoisomers, constitutional isomers, and the conformational isomers. Conformational isomers are the result of rotation about single bond. On the other hand, the molecules that exist with different connectivity are known as constitutional isomers, while the molecules with the same connectivity are known as the stereoisomers. Stereoisomers can exist with no chiral center and with chiral centers. The molecules that exist with chiral centers, they may be enantiomers, may be diastereomers, or may be meso compounds. But the molecules that are having no chiral center generally exist as the diastereomers, and these compounds are mainly considered as cis, trans, or Ez isomers. So now today we are focusing on the methods of determination of configuration of geometrical isomers. So in this we will learn how we assign configuration to the geometrical isomers. How do we know, for example, whether malic acid is cis or trans? As such, there are no hard and fast methods for assigning configuration to geometrical isomers. Generally, we make the use of differences in their physical and chemical properties to assign the configuration. If I would like to sum up here we are focusing, if I am having some sample, so how can I say that this sample is cis isomer or trans isomer? So I have to use its physical as well as chemical properties to consider it as a cis or trans geometrical isomer. Now these methods are classified as physical methods and the chemical methods. Physical methods are dipole moment, melting point, solubility, stability, action of heat, and the spectral properties. On the other hand, chemical methods are absolute methods and chemical correlation method. Here we have to keep one point in our mind, that in absolute methods we generally destroy the identity of the compound, but in chemical correlation method we retain the configuration of the double bond. Very first method to be discussed is the dipole moment. As we know, dipole moment is a vector quantity. It can cancel out in opposite direction if it is equal in magnitude. So therefore, cis isomers have higher dipole moment as compared to the trans isomers. So have a look how it arises. So there are two structures in front of us. First one is cis 1,2 dichloroethene and second one is the trans 1,2 dichloroethene. For cis isomer, the value of dipole moment is 1.85. For trans isomer, the value of the dipole moment is the 0. In cis isomer, chlorine atom is on the same side. So being the vector quantity, it will add to each other. and result in the value of 1.85. In trans isomer, chlorine atom is present on the opposite side or on the diagonal side, so it is cancelling out each other because it is equal in magnitude and opposite in direction. In this example, bromine atoms are on the same side, therefore the value of dipole moment is the 1.35. In trans isomer, bromine atoms are on the diagonal side, so therefore the value of dipole moment is 0. Similarly, since 1,2-diiodoethene is having the dipole moment value of 0.75 and trans isomer is having the value of 0. Next physical parameter that is used for configuration of geometrical isomerism is melting point. It is generally observed that cis isomers are having lesser melting point than trans isomers. Why it is happening? If we look upon the arrangement of the atoms in cis isomer, they follow the pattern of English alphabet U. On the other hand, the trans isomers follow the pattern of the English alphabet X. This pattern of trans isomer is observed more symmetrical and fit more closely in crystal lattice, and this more close packing results in the higher melting point. As it is very clear from this example, malic acid being the cis isomer is having the melting point 131 degrees Celsius, and trans isomer, that is fumaric acid, is having the melting point 300 degrees Celsius. Similarly, cis isomer of cinnamic acid is having 68 degrees Celsius melting point and trans isomer 133. Crotonic acid exists with the melting point 15 degrees Celsius. Its trans isomer having the melting point 72 degrees Celsius. Oleic acid is also having the 16 degree when it is cis isomer and 51 degree as when it is trans isomer. Next parameter is the solubility. Cis isomers are more soluble as compared to the trans isomer. Reason is same, poor packing. Poor packing results in the early solubility. So cis isomers, if we talk about the malic acid, it is having the solubility of 79 gram per 100 ml, and its trans isomer fumaric acid is having the solubility 0.7 gram per 100 ml. Stability is the next physical parameter that is used for the configurational identification. Cis isomers are less stable and trans isomers are more stable. Cis isomers are less stable due to steric hindrance, and steric hindrance exists due to crowding, because the alkyl groups or any other groups that are present on the cis position on the same side, they create crowding in cis isomer, but in trans isomer this crowding or steric hindrance is absent. This crowding causes strain on the cis isomer, and this strain increases the heat of hydrogenation and the enthalpy. Have a look on the heat of hydrogenation of alkenes. General heat of hydrogenation of alkene is minus 120 kilojoule per mole when alkene is hydrogenated or reduced in presence of platinum to the alkane. But if we look specifically, the energy change for 1-butene is minus 127 kilojoule per mole. For cis butene it is minus 122 kilojoule per mole. For trans-butene, it is 115 kilojoule per mole. So 1-butene evolve the greatest amount of heat when hydrogenated, and trans-2-butene evolve the least. 1-butene must have the greatest energy and be the least stable isomer, and trans-2-butene must have the lowest energy and be the most stable isomer. So from this experiment, it is very clear that cis isomer will be that configuration that will release the more energy. This is the energy diagram for the heat of hydrogenation. Here the product is same, that is butane. One reactant is also same, that is hydrogen. Now what is the difference? Difference is the amount of the heat evolved, and this amount of heat evolved is related to the different stability. In this diagram, this 1-butene molecule is at the top position with the highest energy, and trans-2-butene is at the lowest position with the least energy. Next method is the action of heat. If we heat cis-butene dioic acid, that is malic acid, at 160 degrees Celsius, it is easily converted into the malic anhydride. On the other hand, trans-butene dioic acid, that is fumaric acid, sublime on heating at 160 degrees Celsius, but it shows no chemical changes. So fumaric acid forms anhydride via the formation of malic acid, because at high temperature fumaric acid converts into the malic. On heating, cis and trans isomers are interconvertible, and this interconversion takes place as follows. Next, we will use spectral properties as a method for geometrical isomers. Simple olefins like 2-butene does not show remarkable differences in UV spectra. However, cis and trans isomers shows observable difference in the UV spectra. See, still when its cis isomer is having the value of the lambda max is 2800, trans isomer is having 2955. Cinnamic acid with the value of lambda max is 2800, and its trans isomer is having the value 2950. Beta carotene is having the value 4490, and trans isomer is having 4520. Similarly, dimethyl malate and dimethyl fumarate differ with the values 1980 and 2140. After physical methods, we have to discuss about the chemical methods. As we have discussed earlier, the chemical methods are of two types: absolute methods and the chemical correlation. Absolute methods are further classified into conversion into a cyclic derivative, synthesis of a cis isomer, and directed stereospecific reaction. Here, I would like to remind this point once more, that absolute method does not maintain the configuration, they destroy it, but the chemical correlation method have nothing to do with the existing configuration, means their configuration retained as such. Absolute methods can be worked out either one of the three. In first one, we easily convert the functional groups in the cis isomer, as they are located on the same side, into cyclic lactones, anhydrides and amides, but it is not possible in case of the trans isomers. Similarly, in the second one, cis isomers can be synthesized from small rings compounds, but the trans isomers can't be. Simultaneously, E or Z configuration to alkene can be configured by a directed stereospecific reactions. So we will discuss in detail about stereospecific reactions in the last section of this chapter. Means that the stereochemical outcome of the reaction chosen can be confidently predicted. That is, one stereoisomer react preferentially over the another stereoisomer. Here we can easily see that malic acid simply heat by heating at 160 degrees Celsius is converted into the malic anhydride. It is happening because both the COH group are present on the same side and it loses a water molecule very easily. But this feature is not possible in trans isomer as both the carboxylic acid are present diagonally. In this example, this anti-isomer is converted into a cyclic derivative. Why it is taking place? See, due to its configuration, chlorine is in vicinity of this hydroxyl group and it can be eliminated, this part can be eliminated easily and it changes into the cyclic derivative. However, it is unstable and immediately changes into the nitrile molecule. On the other hand, its syn derivative in which this chlorine and hydroxyl group are not in vicinity. So that's why it does not react and it gives the salt in the presence of the sodium hydroxide. Similarly, malic acid can be easily synthesized by the oxidation of benzene or para-benzoquinone. In this reaction, cis-cinnamic acid is easily obtained from one of its derivative, that is orthoamino cis-cinnamic acid. This Wittig reaction witnesses the substantial stereoselectivity and thereby it predicts the configuration of the product, and similar observations are also obtained in the Beckmann rearrangement. In this chemical correlation method, trichlorocrotonic acid is hydrolyzed in the presence of sulfuric acid to the fumaric acid and reduced to the crotonic acid in the presence of zinc, acetic acid and the sodium amalgam. Now, the point to be considered here is that fumaric acid has the trans configuration. So therefore, trichlorocrotonic acid and crotonic acid must also have the trans configuration. So this is not the absolute method. This method is based on the chemical correlation. If one derivative is like this, so its predecessor and successor should have the same configuration. So in next part, we will discuss about the conformational isoarrangement in ethane and butane and cyclohexane. Till then, namaste.